Today's quiz was largely a repeat of what we did in class Monday. This is Wednesday. Okay, we have a pendulum, mass M, tension T, weight mg. Weight directly downward using a level coordinate system. Pendulum is hanging out at an angle phi with vertical. And that corresponds to an angle of 90 degrees plus phi with the x-axis. We draw a free body diagram for this mass with the weight vector mg and the tension vector. Okay, and I didn't label the tension vector, but let's label it here. And we resolve the tension vector into its components. T times the sine of 90 degrees plus phi times the j vector, if we want to make this a vector. Or T times the cosine of phi times j, sine of 90 degrees plus phi being the same as the cosine of phi, and you can work that out by the triangles or just by knowing the circular definition, how the sine and cosine function relate to each other. Okay, the horizontal component of the tension is T times the cosine of 90 degrees plus phi, or negative T sine phi, and those would be vectors expressed as vectors. Those would be expressed as multiples of I. The vertical and, well, you have vertical equilibrium. The pendulum pretty much moves back and forth along the horizontal. These are approximations now for small angles. Assuming phi is a small angle, and that was part of the assumption. The T cosine phi, the magnitude of this vector, has got to be equal to the magnitude mg of this vector. And I labeled this mg j, should be mg times negative j. If we solve for t, we find this mg over cosine phi. If the angle is small, the cosine phi is close to 1. To the extent, the smaller the angle, the smaller, the closer cosine phi is to 1. In any case, you get something very close to mg over 1, or mg. So the tension is mg. And the vertical component, the tension, is approximately mg. It follows, and I've got a little note there, cosine phi is approximately 1 when phi is small. You can see that from a triangle with a small angle. Thus, your net force is negative T sine phi times I. In other words, you're just left with this. Now, in the diagram, I've replaced the T vector with the two component vectors, this one and this one. This one being opposite to this one, these add up to 0, and we're just left with this one, which is your negative T sine phi times I. And that's negative mg sine phi times I. Then the acceleration is going to be the net force divided by the mass, and that net force isn't constant. Okay, net force depends on phi, which changes with position. As the pendulum changes position, net force changes. And it's the sine phi, so as phi approaches 0, the net force approaches 0. The bigger phi is, the greater the force. So you have a decreasing force as the pendulum swings from any point toward equilibrium. A force of decreasing magnitude. That's going to give you a changing acceleration, and it's a changing acceleration, so you cannot use the equations of uniformly accelerated motion. And I was careless, I wrote can instead of can't. So let's be sure we can't use the equations of uniformly accelerated motion for the reason that the force is not constant, so the acceleration is not constant. Acceleration is not constant, You don't have uniformly accelerated motion. Emphasize that. I don't want to see anybody using uniformly accelerated motion with a pendulum. It's essential to understand this. Okay? Don't want you to cause yourself all the pain you get by not getting any credit on a problem because you used uniformly accelerated motion when it wasn't uniformly accelerated. Okay. We have an incline with a slope of alpha. Okay, well, same situation we looked at previously, but I'm going to go into a little more detail about the relation between the slope and the angle. Okay, now I say that if the slope is alpha, then the angle is alpha, or very close to alpha, if you have a small slope. Let's see why that is. The slope is the tangent of the angle of the incline. Why is that? Well, here's your incline, here's your angle, and here's your rise, and here's your run. Well, your rise is the opposite side, the run is the adjacent side in relation to the angle phi. So that the rise over the run, which is a slope, is equal to the tangent of phi. So taupe is the tangent of the angle of incline. It always is the tangent of the angle of the incline. Now, why is that approximately equal to alpha? For small slope, for small phi, in other words, or small alpha, for small phi, the tangent of phi is sine phi over cosine phi, and of course, cosine phi is close to 1 when the angle is small, so that the tangent of phi is approximately equal to sine phi. Sine phi is approximately equal to the angle phi. Okay, very important result from basic pre-calculus, or just a decent trig course. So, if sine phi is approximately equal to phi, and tangent phi is approximately equal to sine phi, and tangent phi is equal to alpha, turns out that phi has to be equal approximately to alpha. Put all that together, it's pretty simple. Okay. Now, didn't quite have enough room to do all this, but it should show up pretty well in the video. We have an incline, again, with a ball on the incline. We have mg, the weight vector, acting downward. We have normal force vector acting perpendicular to the incline. Now, on at least one quiz, I saw a vertical vector, pretty good sketch, but a vertical normal vector. That's not right. Normal vector is not vertical unless your surface happens to be horizontal, and this incline is not a horizontal surface. See, so I'd recommend that you sketch your normal curve and carefully sketch an x-axis parallel to the incline and a clearly labeled right angle so that you know you're looking at a reasonably accurate sketch that won't mislead you into thinking that the normal force is vertical. Okay, now it often is if you're sliding an object along a level surface, then the normal force that gives rise to the frictional force is vertical, and that's probably the first normal force you encounter. Okay, and in the mastering assignments, the first few normal forces were with level surfaces. But then you had inclines, other situations where the normal force was not vertical. So you need to move past the first introductory steps, and those are good problems, to the more general problems. Okay, by understanding what a normal force is. It's an elastic or compressive reaction of a surface to a force exerted on it, and it's always perpendicular to the surface. And we demonstrated that last time with the meter stick. Remember, we held down the meter stick and then released it, and the object on the meter stick didn't go vertical, it went perpendicular to the meter stick. We got a projectile motion out of that. Okay. So we can draw now the free body diagram using the natural coordinate system, which is tilted, and that has the advantage that the motion is along the x-axis. And also conveniently, the normal force is going to be along the y-axis. But the key is, if the motion is along the, if the motion isn't along your x-axis, then you're analyzing motion in 2 dimensions. You can reduce it to 1 dimension by choosing a tilted coordinate system with the x-axis parallel to the incline. Ball's constrained to move on the incline. That's where your x-axis ought to be. Okay, so we draw a free body diagram. Here's our mg vector. It's now at angle alpha with the y-axis, with the negative y-axis. Why? Because this thing is tilted at angle alpha. I haven't labeled the angle here. It's just labeled here so it doesn't hurt a thing to go ahead and label it here as well. So we can kind of do this. Okay, so we see that the incline makes angle alpha with the horizontal direction. And if we have a y-axis here, this angle has to be the same as this. Why? Because the y-axis is perpendicular to the horizontal, and the incline makes angle alpha with the horizontal. And the negative y-axis here is perpendicular to the incline, so you put all that together and you can make a good argument. And it's also obvious. If you just think of gradually tilting this thing, what happens? The y-axis swings out from the mg vector as the horizontal axis goes from here to here. It causes the y-axis to swing out from the horizontal vector, from the vertical, at the same angle, the angle of rotation, which is alpha. So you can kind of think about that, think of it in those terms if you wish. Okay, anyhow, establish this is the angle alpha. So we can label this angle as 270 degrees plus alpha. Now, alpha is the slope, which is unitless. So this alpha is unitless, which means it automatically represents an angle in radians, and we're adding that to an angle in degrees. So you got to either, if you're going to do a calculation with this, you've either got to express alpha in degrees or 270 degrees in radians. You do either. It's easy. Okay. Here we have our diagram again. Okay, mg's down, normal forces along the y-axis. We resolve the mg vector. We get mgy times negative j and m times gx times negative I. And we resolve these using the same ideas that we used over here. So I'm not writing those down, but gy is going to end up being g times the cosine of alpha, and gx is going to be g times the sine of alpha, and then the mgy is going to be multiplied by negative j, the mgx by negative I. You work out the details and get the specific expressions. Equilibrium in the y direction, well, we do have equilibrium in the y direction. Why is that? Because the ball moves along the x-axis. It's not accelerating, it's not even moving in the y direction. Equilibrium means you got zero acceleration. So we have equilibrium in the y direction, but not, of course, in the x direction. The equilibrium in the y direction implies that these two forces be equal and opposite. So the magnitude of the normal force is going to have to equal the magnitude of gy, and I've got to take this call. So I'll pick this up in a minute. I don't have to take this call, that's a telemarketer. Okay, not crucially important, but a kind of important call that I do have to take if it comes in. Okay, back to this. Equilibrium in the y direction implies your normal force is m times your gy. Your gy is mg times the sine of 270 degrees plus alpha, or mg times the cosine of alpha, just back to this diagram. I use the 270 degrees plus alpha so you don't have to think about the signs. SIGNS. Or use the alpha and worry about plus and minus signs. And with the cosine. Either way, it comes out this way. The magnitude is mg times the cosine of theta. And actually what I wrote here is incorrect. These are magnitudes. There are no arrows over them. So actually we should have the magnitude of the sine of 270 degrees plus alpha. Okay, well, we get all this. So in the x direction, your net force is what? Now, again, you got the normal force here. You don't really need the normal force because we don't have friction, but in another extension of the problem, we do have friction, so we do want to be able to calculate this. Okay, so these forces are equal and opposite. The net force then is just a force in the x direction, which is negative mg times the sine of alpha. And you can get that from the diagram. Here's your triangle. Here's alpha. And here's the magnitude of this vector times the sine of alpha. The negative x direction, so the negative sign. Now we're equipped to figure out the acceleration. The acceleration is in the x direction. It's F net x over mass, which is negative g times the sine of alpha. Now that's an equation that people use all the time without thinking about where it comes from, because it pretty much applies to any incline at angle alpha if you don't have friction. It even gets used if there are other forces. And, you know, it's not an equation that always applies to the acceleration in the x direction. If there are other forces, then they have to be taken into consideration to get the net force. And they're going to give you something along with the negative g sine alpha. You got to be careful about that. Okay, it's gotten long enough. We got the thing about the rotating beam. We'll get to that in another shorter video.